Hello everyone. Today we are presenting our project on designing a fluent torrent distributed payment system. This project focuses on building a reliable and high available payment system that can continue working even when some part of the system fail. Now, this project was developed by our team members. Wickramasinghe G.K.D.K is our team leader, and Wijesinghe and others are Yavindi, M.D.C, and Perera K.K.T.L. Each member focused on a key component of the system, and finally, we integrated all the parts into one complete solution. Now we will move to the introduction. In modern e-commerce platforms, payment systems must be available 24/7 hours and handle transactions accurately. Even a small failure can lead to serious issues like payment loss or incorrect records. To solve this, distributed payment systems are used. They allow multiple servers or nodes to work together to improve reliability, availability, and recovery. In our project, we design the system that ensures payments are processed correctly even during failures and network issues. When we talk about problem statements, there are several challenges in existing payment system. First, that must be available all time without interruption. Second, payment data must always remain correct and accessible from any server. Third, the system should continue working even if some nodes fail. And finally, all events must be properly ordered across the system. Our project aims to solve all these challenges using a distributed approach. Now I cordially invite Tamod to continue this presentation.
Our solution is a distributed payment system designed for reliability and consistency. We use three nodes, so the system continues even if one fails. It follows a leader follower model where one node manages decisions. We implemented heartbeat monitoring to detect failure quickly. All payments are replicated across the nodes, ensuring strong consistency. We use HLC hybrid logical clock for proper time monitoring. Consensus is handled using Raft, so all nodes agree to transactions. Overall, this ensures high availability and reliable payment processing. Our system is built using four main components. First, fault detection and recovery handles the node failures. Second, payment replication ensures all nodes store the same data. Third, time synchronization keeps transaction order correct. Finally, Raft consensus manages leader election and agreement. Each component was developed separately and then integrated into one complete system. Now I will explain the main design decisions behind our system. For the backend, we use Go to handle distributed nodes and failover efficiently. The front end allows user to input payments and monitor system status in real time. For consistency, we use quorum-based replication to ensure accurate data. For timing, HLC helps maintain correct event order. For agreement, Raft ensure proper lead election and consensus. These design choices help us achieve a system that is both reliable and scalable. Presentation will continue by Dahamya.
So the main goal of this module was to make sure the system continues operating correctly even when a node crashes, become unreachable or experience a temporary network delay. To achieve this, each node sends a heartbeat message every 2 seconds to the other nodes. So if a node stops responding, it is not marked failed immediately. Instead of that, we use three-stage model: alive, suspect, and failed. So like after 10 seconds without heartbeat, the node becomes a suspect, and after 20 seconds, it is marked as failed. So this design helps reduce false positives caused by brief network issues. So once a node is confirmed as failed, the system applies automatic failover. Then requests are redirected to healthy node using round robin strategy. So it prevents one backup node from handling all redirected traffic. So if the failed node later rejoins and starts sending heartbeats again, it is marked alive immediately. And the replication module is notified so that its payment data can be resynchronized. We also implemented a gossip protocol. So this allows failure information to spread quickly across the cluster. So instead of waiting for every node to detect the same failure independently. So in addition, if the failed node is currently the leader, the fault detector notifies the consensus module so the Raft can begin re-election. And Finally, the test results show that all the major fault tolerance scenarios are passed, so including heartbeat flow, suspect detection, failure detection, recovery detection, gossip propagation, failure redirection, status monitoring, and self-heartbeat prevention. All this confirms that the module behaves correctly during both failure and recovery situations. So the next part will be done by Kunjana.
Thank you, Dhammya. Now I will explain my part, which is data replication and consistency. The main goal here is to ensure that payment data is never lost and is always consistent across all nodes, even if some servers fail or become unreachable. To achieve this, we use content-based replication. This means payment is sent to multiple nodes, but is confirmed only when majority of nodes agree. This approach improves both speed and reliability because we don't need to wait for all nodes. We also use Wijesinghe fluent tools, which means the system can still function correctly even if some nodes fail or behave unexpectedly. Now we will move to the next slide. Consistency model. For maintaining consistency, we use the last right wins algorithm. In this method, if multiple updates happen at the same time, that one will with the highest version number is selected. If the versions are equal, the system uses time steps to decide the correct value. This ensures that all nodes eventually reach the same consistent states. Duplication and retry protection. This is another important feature. Duplication. Sometimes due to a network issue, the same payment request can be sent multiple times. To prevent duplicate changes, the system tracks transactions ID for 5 minutes. If the same request received again, it returns the previous result instead of processing it again. This generates extractly once execute the payment. When we talk about performance optimized, confirmation on majority absences achieves 3.8 milliseconds average latency and 40% of improvement over traditional full replica synchronization method. When we talk about integration with consults, works seamlessly with graph validation fluid detector to identify live nodes and clock synchronization for consistent time steps across the entire cluster. Now we will move to the next slide. To eliminate the bottlenecks of traditional systems, we implemented a sophisticated quantum consensus and parallel replication model. Rather than waiting for every node to acknowledge a transaction success is confirmed once a majority voting is achieved, significantly lowering latency while maintaining Wijesinghe fluent model. This runs through a clear four-plus extension pipeline. It starts with extension at the leader node with the unique ID. When then handle the identification of all live response nodes, next is a parallel display. Propagation transaction simulators lead to available nodes using quorum acquire routing. Finally, we return success immediately upon majority confirmation, avoiding the wait for total store replication. Now we will move to the next slide. Let's look at how the process impacts performance. As you can see our 3-node quantum replication achieved an impressive latency of just 3.8 milliseconds. This is very compliant with our SLA of under 10 milliseconds and represent 40% of improvement over traditional signification method. Finally, to validate my components, we conducted rigorous credential testing across 6 key scenarios, including complex devices like network partitions and partition node failures. As shown in the table, all test cases passed flawlessly, confirming that our approach generates system robustness and determination concurrence. Now I will invite Chanvi to continue the presentation. Thank you.
Thank you, Kunjana. Now I will explain my part, which is time synchronization. My role was make sure timestamp remain accurate across all payments nodes and that payments events stay in correct order. This is important for auditing, debugging, and reconciliation, and preventing incorrect transaction order caused by clock drift. Design choices. To achieve this, I use NTP style synchronization to reduce clock drift between nodes and hybrid logical clock, or HLC. To preserve event ordering, physical time alone is not enough in distributed system. So HLC added logical ordering on top of the physical time. I also included fallback support so the system can continue working if external synchronization is temporarily unavailable. How time synchronization is working? The module works by periodically update each node's local clock offset. When a payment event occurs, the system assigns it its HLC's timestamp. The time endpoints expose the current reference and synchronization state. The system also detects clock skew between nodes and records delayed event using HLC. Timestamp before the final login. Even if synchronization is lost, local counters still preserve the correct order. The result. To validate this module, I tested offset calculation, delayed validation, timestamp corrections, queue detections, out of order recording, background synchronization, recover after synchronization lost, multi-node alignment, and payment event correction. All the test cases passed successfully, which confirmed the module maintained correct timing and event order. Time synchronization summary. The synchronization improved reliable and auditable for payments log. Physical clock alone are not enough distributed system. So HLC prevent perceived clock casual ordering even when clock drift. The system also remains functional during temporary synchronization failures. Next, the presentation will continue. Kamod.
My part focuses on the consensus mechanism, which ensure consistency and reliability in the distributed payment system used in the raft algorithm. In lead election, all nodes start as follower. If they don't receive a heartbeat, they become candidate and request votes. A leader is selected only with majority votes. The heartbeat mechanism is used by the leader to maintain control and prevent unnecessary elections. For rights, we use majority-based approval, meaning transactions are accepted only when most nodes agree. In log replication, the leader sends updates to all followers, ensuring all nodes stays synchronized. For client handling, only the leader processes requests, while followers redirect clients to avoid conflicts. In failure handling, if the leader crashes, a new leader is automatically elected. Nodes communicate using UDP, allowing fast coordination through message exchange. One limitation is that we use in-memory storage, so full persistence is not implemented. We validated our implementation through multiple test cases. All core raft functionalities such as lead election, vote handling, and log replication passed successfully. We tested split vote scenarios, and the system correctly triggered new elections. Append entries test confirmed both successful replication and retry handling. Majority commit validation ensured operations only proceed with enough acknowledgements. We also verified node failure detection, where the system re-elects a leader after missed heartbeats. Overall, all tests passed, confirming that our system is reliable and fault tolerant. The presentation will continue by Chanumi.
Thank you, Kamol. During the deployment, we faced some important challenges. First, there were merge conflict in main Go because all four members need a startup code in the same file. This was solved by combining both HTTP and UDP layers into undefined entry point. We also found self-heartbeat paths, not represent it on start and prevented timeout detection. And these are force fixed in self-ID checks. Another issue was missing startup grace period, which caused nodes to be marked fail to earlier, so we added 30-second grace period. We also faced leader transition after leader failure, which caused repeated election instability. This was mainly due to election timeout, misconfigurations, in draft module. Another challenge was UDP reliability, since UDP does not guarantee delivery. So reliable was handled at the application level using acknowledgement and majority-based decision. We also observed that payment records were lost after the full restart because storage was memory only. Showing these percentages. Result and observation. After addressing these issues, the system shows strong result. It remained available even when one node failed because healthy peers continued processing payments. The three-stage detection modules eliminated false positive during the testing. Quorum-based replication ensured payments were not lost during the partial failures. HLC ordering kept even consistent across nodes, and draft leader election restored the right path after leader failure. Overall, all four members were integrated successfully into stable and reliable system. Next, I will continue this presentation to the hangar.
So As for future improvements, we identified several ways to make the system stronger, such as supporting dynamic node addition and removal without restarting the cluster. Also, like building a live web dashboard for node status and gossip events, and scaling beyond 3 nodes, and also replacing in-memory storage with a proper embedded database. So, in conclusion, we highlight that the system successfully achieved its 4 main goals: fault tolerance, data replication, time synchronization, and consensus. So the final result is this. The final result is a distributed payment system that remains available during node failures, keeps payment records consistent, preserves correct event ordering, and automatically recovers leadership when failure occurs. So overall, the project demonstrates how distributed system techniques can be combined to build a reliable and practical payment platform. So let's take a look at our distributed payment system. So from here you can send a money transaction. Here are node status, and here it shows the current leader. And also here's the time synchronization panel, and here you can see the stored or money transactions. So let's send a money transaction here. So here you can see a payment successful message, and here it's successfully stored. And also, if you kill the leader node, another node will immediately choose as a leader. So also you can restart the node.